Следующий докладчик Вера Алексеевна Муракашева, и название доклада «Существование глобальных фундаментальных решений для одного класса уравнений Фокера-Планка». Well, the next speaker is Vera Alexeyevna Murkasheva, and the title of the talk is Existence of Global Fundamental Solution to a Class of Fokker-Planck Equations.
Thank you very much. I would like to thanks to the organizers for the kind invitation. And my talk is Existence of the Global Fundamental Solution. So the first what I'd like to do is to pose the problem, then to describe a little bit the state of arts, and then I would like to explain the sketch of the proof on a very simple example and very popular ones. And if I will have time yet, I think that I can describe some motivation which to do this job. So let us consider the Fokker-Planck equation. It's a parabolic type equation where we have the vector fields x and y. Vector fields x is a fields which are posed in this way, and y just have a different coefficient, or the same, it's not right now important. And these vector fields must satisfy these four conditions. First of all, these vector fields must be smooth. The second is that them vector fields x must be homogeneous with degree 1 to the corresponding dilation function, and the vector field y must be homogeneous of degree 2 to the same function. That means that if we do this substitute, so each coordinate in our space has the multiplier, then and then we take derivative with this coefficient on this function with this argument, then we have the following expression. And here we have lambda in degree 1, and here we have lambda in degree 2, which means exactly the homogeneity of these degrees. Then the next what we need to ask from our vector fields are the rank condition almost everywhere, and the last condition is that our set of vectored fields must satisfy Hermander hypoellipticity condition with degree n, which is the dimension of the number of our variables, like xn, x1, x2, xn. So the question of the solvability of the equation what we have proposed at the beginning is equivalent to the question of the existence of the global fundamental solution to the corresponding differential operator of a second order. What we can say right now, this operator is linear, it's a parabolic type, and it's very degenerate subelliptic stationary part we have inside. That means that for these vector fields, we have the characteristic form which is non-negative and could be very degenerate. That means that, for example, if we have Rn with n equal 100, for example, 100 coordinates, and we have equation for only for 3 of them, it's already not enough, like not enough information. And so that's why such type of equations could be understandable as a very degenerate one. And the key idea or how to work with these equations, I think that any engineer will will answer that what you need is to find the change of variables to make this equation to be linear with constant coefficient. And then you can solve it easily, as usually we do. And then you do the opposite change of variables, and voila, you have the solution. But it's not so easy in this case, because we can do such change of variables only locally. And that's why we have only we can construct only local solutions, fundamental solutions. And the question is when and why we can obtain the global solution. So, so there is the approach. This approach, what I was talking about, is a Levy parametrics method to construct directly the local fundamental solution in the neighborhood of the point. And then you can use the saturation technique. That means that you, for example, can make a step from the heat kernel to the fundamental solution of the associated stationary operator, or the step from the solution for the Laplacian of the high degree to the solution of the Laplacian which has less degree. And the third technique, small method, it's a lifting method. It's already connected with the sub-Riemannian geometry, and the idea is that you can use this method to change the homogeneity and left invariancy of the operator, and using the special technique, I would say, which was described in the very famous paper of Rothschild and Stein. So what I want to stress one more time is that usually the existence of a global fundamental solution it's more difficult to obtain, and I would like to discuss first the papers which are devoted to the local fundamental solution with or without explicit formula, and then only a short list of ones which belong to the which are talking about the global solution without or with precise formula. So the first, I want to list the work of Levy. It's a very old work where he has done this first time proposed this method to construct for any totally elliptic equation the parametrics, which is local fundamental solution. And then we can speak about the textbook of Friedman about differential equations of parabolic time, and very famous for the sub-Riemannian settings, the book of Hermander, which and about the analysis of linear partial differential equations with not stationary coefficients. And the last one is a fresh monograph of Kalin, Chang, Furutani, and Iwasaki about heat kernels for elliptic and subelliptic operators, where one can find a lot of examples and very deep and large and structured list of literature of references.
Subelliptic is the same as hyperelliptic.
Yes, there is hyperelliptic. Not exactly. No. I will show, in an example, it will be clear why it is not the same and what is the difference, I think. So, about the Levy papers, which can give you the local fundamental solution via the parametrics method. You can, I want to stress the paper of Citti and Manfredini, because I have obtained my inspiration from the papers of Citti, exactly in near vision. And they were talking about the local fundamental solution for the subelliptic, specific subelliptic operators. And then it's interesting to stress this work of Bramanti, Brandolini, Lancanelli, and Uguzzoni about the equations and about heat kernels of some parabolic equations of parabolic type with in sub-Riemannian settings. And then Bramanti, Brandolini, Lanfredini, and Perdoni, it's also not so, it's also fresh work, and it's interesting because they are working with not smooth coefficients in the vector fields. Sorry, I have no time? 5 minutes. Okay. So I need to go through global fundamental solutions. First, I need to stress the job of Folland. He has a multitude of results about subelliptic vector fields and subelliptic manifolds and estimates of functions on these groups. And then the paper of Nigel, Ricci, and Stein about the fundamental solution for sublaplacians, and then maybe this one, and the most important is the Bianchi and Bonfilioli, the last one in 2016, because my job was based on the technique what was developed in this last paper. And the main theorem is that for the set of vector fields that satisfy the condition I've been talking before, there exists a global fundamental solution for this operator, and this fundamental solution is smooth enough, and it is invariant with respect to the shift and have a lot of good properties. And basic example. So let us consider the vector field x1 like this, and the vector field x2 like this with the width. What we can tell about this? If we like to construct here the sub-Riemannian metric space, then we obtain the geometry where the distance will be not the direct line, but something like this curve. Why it is so? Because if you have a point here and push it, then this point cannot go directly in this direction because of this width. If you close to x equals 0, then it means that it's difficult to go up, and it's much more easier to go down. That's why point is going down, and then only have the possibility to go up. This is an easy explanation why the geodesics in this metric, why geodesics looks like this curve. They are not direct. So what I would like to say, that these vector fields are homogeneous of degree 1 with respect to this function, this dilation. And condition holds, and we can construct on R2 a Lie group. And these vector fields are satisfying the Hernando-Run condition, and that's why the Hernando operator and the sum of squares of these vectors, the same as Kolmogorov type operator, this vector and plus this without any square, they both are hyperelliptic. But there is no Lie group structure on R2 to make this operator to be left invariant with respect to the shift in this group. And that's why this operator is not sub-Laplacian, and we do not have Yes, but they are hyperelliptic, but not sub-Riemannian manifold we have. We have only metric space. This construction is the same, but the quality is lost. So what should we do? For the Hermanter operator, the normal thing to do is to lift it. This was what found out Rothschild and Stein, and then Folland has developed for such kind of operators. And we have decided to lift also this Kolmogorov type operator to find what we wanted. So this is what I have told, and in the considered Grushin example, we can use directly the technique which was developed in the paper of Bonfilioni Bianchi and based on Folland research. And so what should we do? We do the global lifting to the homogeneous operator proved by Folland in '76, and we have the Carnot group G, and the surjective polynomial map P from this group to R2, our metric space, such that the operator, Hermander operator with squares of vector fields, I have not, I'm sorry, 1 minute more, just to, on this slide to stop on here. So yeah, our operator is transformed, is P-related to the sub-Laplacian on the group G. This sub-Laplacian means that we have a sub-Riemannian manifold G, and this operator is, lift means that our vector fields are transformed. We have one more variable, that means that we obtain the saturation. In reality, we saturate our problem for one more variable. And so constructed like this, we can obtain the operator, which will be Fokker-Planck, but it will be left invariant and very good. So we can obtain the global fundamental solution for this lifted Fokker-Planck operator. And then from it, we can directly construct by integrating the fundamental solution for the Fokker-Planck for the initial problem. So that's the idea. Thank you. I'm sorry.
Unfortunately, there is no time for questions, so let us
No time for question, but in next such conference, we give you more time.
Да, это в карман.